Okay, good morning. People weren't kidding, you really are blinded up here. I am very pleased to be here and to share the work that AGIL's been doing over the last year. We'll cover a variety of topics today, but I want to dive right in with milking speed first. So in October of 2021, the CDCB Board of Directors appointed a task force to investigate the feasibility of implementing genetic evaluations for milking speed in the US. And we meet regularly in progressing towards this goal. Now, last year at this meeting, we presented these 4 research objectives to you all, and today I'd like to give you an update on the progress. And these objectives really encompass the final goal of standardizing a trait definition for milking speed using quantitative data coming off of inline milk meters. And of course, characterizing and accounting for system or milking management effects as well as biological conditions that can impact that phenotype. So the first step in doing this is assembling a data set that can help us answer these questions. So I'd like to extend special thanks to Robert Fordrain and John Clay at DRMS, who have gone to great lengths to make this type of data available to us. So the type of data we're working with comes from just over 300 herds. It includes 230,000 cows and ultimately over 40 million observations. And the reason for this is because we're working with milk weights and milk durations from every single milking in a day and every single day in a cow's lactation. And so this data becomes exponentially large quite quickly. But this does also describe data from over 31 states, multiple dairy breeds, as well as multiple OEMs or original equipment manufacturers, meter manufacturers, some of which are also robotic systems. Now, this slide is showing an example of some of the really important first steps in parsing how system effects and biological conditions can affect these measurements. So there's a lot happening on this graph here. I'll break it down for you really quickly. So on the y-axis, milking speed is the phenotype we're working with. That's the total milk weights from that particular milking divided by the total number of time the milking took in pounds per minute. The banners across the top there are showing the different meter manufacturers. The banners on the right-hand rows with the number 2 or 3 are showing milking frequency. We're only working with non-robotics data at this moment. And this is just showing data for Holstein and Jersey, for whom we have the most representation in our data set. Holstein is indicated by the red line and Jersey by the blue line. And then, of course, across the x-axis, you have day and milk. And probably the first thing you'll notice is that Bico and Yantek herds that milk at a 2x frequency aren't represented in our data set at all. We simply just don't have data available for them. Similarly, if you were to look at Bomatic herds that milk with a 3x milking frequency, and I'm sorry, I'm going to have to move so I can remember what order my slides are in. You'll notice probably most starkly that the Holstein line here is quite smooth, and that's representing data from over 22,000 cows. So remember, the 40 million observations is related to milkings themselves. That number becomes substantially reduced when we talk about the number of animals represented in the data set. And Jersey, who have a much less consistent line here, represent data from only 167 cows. And so this is one of the major challenges we deal with, where the more we stratify this by things like parity, breed, milking system, milking frequency, we do start to encounter a lot of sparsity in the data. And that does make it more difficult to elucidate trends. This is a challenge that's likely to continue to be relevant as we move forward in collecting data on a large and national scale. However, overall, if we look at these trends, we do see that milking speed tends to mirror the milk production curve as we move through the stages of lactation. This is to be expected given the moderate to high correlations we see with milk yield, both observed in this data set and reported by other independent studies in the literature. Now, a really important question the task force is focused on is whether automatic milking systems, AMS, or robotics herds can be evaluated together with conventional herds. So this graph here is showing information for Holstein only. Again, we have the most data for this breed, so it's easiest to examine trends. You have that same phenotype of milking speed on the y-axis and day in milk across the x, but this time it's OEM that's represented by the different lines. And again, we see milking speed more or less mirroring the milk production curve. What is quite interesting is at first glance, De Laval, indicated by blue, and Lely, indicated by the red line, have quite different milking speeds. And I want to caution everybody that this does not suggest cows milk more slowly on a de Laval system. This is an artifact of how each OEM measures milking duration. When we talk about a robot, the classic example would be box time, total time in the robot, versus milking time, the moment that the unit is attached. And so this is simply to say it's a demonstration of an OEM effect that will need to be accounted for when we're talking about harmonizing data from diverse systems and sources into a single evaluation. Now, the task force has also focused on the relationship of milking speed to other health parameters and extended that to other milk components. And so the approach for this is to average milking speed for all milkings on a test day, and then correlate that directly with the reported somatic cell, fat, and protein on that same respective test day. And the average milking speed for the day is required because we don't know which day or which milking in our data set was used for the test, depending on what plan the herd was on. And so if we look more closely just at somatic cell score for an example, we do see that there is a weak but favorable correlation between the two. And in a similar analysis, we saw that there was no statistically significant association with clinical mastitis diagnosis on the same exact day that the milking speeds were reported. And these results for somatic cell and clinical mastitis are a little bit at odds with what we had expected, given prevailing theories about milking speed being tied to cows that have more mastitis problems, and other reports in smaller scale studies that we've seen in the literature. And one of our theories here is that right now we're treating milking speed like it's a linear trait, and maybe we need to be evaluating it in terms of standard deviations from the mean for that herd. And that maybe any mastitis complications related to cows milking extremely slowly or extremely quickly are being masked by lumping them all together in this quantitative correlation. So some of our next steps will be to look at those extreme groups and see if these trends still hold. Now, what's next on the horizon for milking speed? It's in generating PTAs and heritabilities so we can make a recommendation to the board about how to move forward with this. And so we're very excited. We do have some preliminary data to show in this regard. So we're first taking an average milking speed trait using all available data. So this is an individual cow's average milking speed over all her milkings in a day, every day in her lactation. And we're using complete lactation data only, starting with Holstein and Jersey animals. So this was a sample size of about 20,000 cows, representing data collected over just 1 year. And the heritability for this trait was 0.37, which is encouragingly high. We also examined genetic correlations between this milking speed PTA and somatic cell score, milk yield, and net merit. Now, this is actually an antagonistic correlation, genetic correlation between milking speed and somatic cell score, again, different than the phenotypic correlations I showed on the previous slide. So this here is suggesting that if we're selecting for cows that milk faster, they do tend to have higher somatic cell score. Something that the task force found exceptionally encouraging was the low correlation with net merit. That, especially in concert with the high heritability of the trait itself, suggests that there's a lot of value in a genetic evaluation for milking speed, and that it's bringing something new to the table that's not already being captured in the traits currently included in net merit. And the last thing I'd like to point out here in this example data is that the mean reliability for Holstein bulls was 0.67, but this number ranged all the way up to the high 80s. And this was simply a function of how popular that bull was in our data set and how many daughter records we had available. So next steps here will include examining alternative phenotypes. So one of them being average milking speed, but only from test day data only. This would represent a possibly more feasible approach to capturing this data on a large national scale. The high resolution of every single milking and every single day for every day of a lactation would be a major challenge to have that data flow into the database, whereas adding this to the test day data in the current format where it already flows would be a practical and hopefully expedient way to start collecting this data. And then, of course, we want to examine how heritabilities and PTAs for this trait change using data from primiparous cows only. And this is because our European counterparts, who have evaluations for milking speed based on a subjective categorical scoring system, use data typically only from primiparous animals. Now, that was a very quick overview. The next topic I want to talk about in the time we have here is work we're doing to account for identical animals and clones in genetic evaluations. This is slated for implementation in the December 2023 official evaluations. So how does data about clones reach us in the first place? It's through multiple birth codes. So out of about 7 million genotyped animals, we have nearly 5,000 pairs of natural identical twins, over 1,700 split embryos, and 530 nuclear transfer clones reported to us. So why are we concerned with clones when they make up such a small proportion of animals? The reason is because they multiply the genetic contribution of highly influential animals to the total population. So a good example of this would be considering Apple, who won World Dairy Expo Grand Champion in 2011. She was cloned 9 times. And 2 years later, in 2013, she was beaten by one of her clones for Grand Champion here at Expo once again. Now, Apple herself, the font's a little small here, she had 361 progeny, but her 9 clones altogether added another 325 progeny, effectively doubling the genetic contribution of a single animal to the population. So this is an example of how we want to improve accounting for identical animals. So what did we change? Well, previously the pedigree matrix treated clones as full siblings, but this did lead to an underestimation of pedigree inbreeding. So now the new model stores a source animal for each identical group, and then during the computation of the evaluations, it switches the dam sire ID to this source ID. And what this allows us to do is acknowledge that the animals are genetically identical, but store and keep a separate permanent environment effect for each clone. And so an example of these impacts and results, courtesy of Paul Van Raden, are shown on the right here. So if we consider a calf born in 2020, whose maternal great-grandsire was a clone of the paternal second great-grandsire, in this case it was Manoman and Manoman 2, we found that originally the pedigree inbreeding estimate was 9.8%, because again, it was treating her ancestors as full siblings, not identical animals. Now with this edit, it's been corrected to closer to the true value of 10.6%. And her genomic inbreeding remained the same at 13.5% because, of course, the genotypes themselves are identical. So again, this work is slated for implementation in December of 2023. Now, the next topic I want to talk about is work we've done for standardizing, improving our standardization of lactation yields and the factors used for those estimations. This is also slated for implementation before the end of the year. So how do we measure and compare yields in the first place? Herds who are interested in knowing their yields traditionally participate in DHI testing. A technician travels to the herd and samples part of her yield from one milking in a day. From that single milking, her total daily yield is extrapolated. From that, her total lactation yields are predicted. And then when it comes time to draw fair comparisons across cows performing in different environments, we calculate their 305-day mature equivalents, or 305 MEs. Now, the last time these 305 MEs, the methods for them were estimated was in 1994. And at that point, we performed corrections for parity, age, season of freshening, previous days open, geographical region, and all standardized to a milking frequency of 2x. But we know that genetic selection changes maturity patterns, so after 30 years, it's time to re-estimate these factors. So the data we worked with for this research comprised over 100 million milk and fat lactation records, and just 81 million protein records. The reason for that being we're using historical data and we haven't been collecting information on protein for quite as long. We did not change anything about standardizing to 2x milking frequency or how we're accounting for previous days open, but we did make a lot of improvements to our assessment of season region effects as well as age parity effects. So previously, season region or the region effects were calculated across 3 geographical regions representing the East, sort of the Midwest and the South together, and the West. Now we've defined 5 new climate data-based regions, hopefully better capturing seasonal effects on yields. Previously, these calculations were done within breed individually. Now they're done with all breeds together. Now when we consider age parity, previously age group within parity was how these animals were accounted for, so they were grouped into young, medium, or old within each parity group. Now we're using a more quantitative measure of age in months. And probably the biggest change here is that previously these were standardized or corrected to mature age for each breed. We're now correcting to average age of 36 months. This has been the standard of the traditional PTAs since 2005, so that makes these new 305-day estimates more in line and more consistent with other metrics we're providing to the industry. But it's also more reflective of the cows that producers are actually seeing in their herds, given that very few animals actually reach mature age. I want to give a quick overview of these new climate-based regions. So the U.S. Department of Energy reports climate zones 1 through 8 at the county level, and these are publicly available online and usually used for building codes, insulation, that type of thing. So what we've done is we've averaged these county codes by state and then used that to group states into the overall hottest, indicated by the red there, to coldest regions in the U.S. One of the most burning questions I always get about this slide that I'll just answer now instead of waiting till the end is, why did we average by state instead of using something more like county level resolution? And the biggest reason is we're using historical data, and county lines change over time. So it's not necessarily true that that county will apply to the historical data. And also often the records, the address we have on file is the address of the home of the owner, not the location of the herd. So we can examine these factors graphically. Again, there's a lot happening in this plot, but the regions of hot, again in red, all the way to coldest in dark blue are indicated by the banners across the top. Corrections for milk, fat, and protein are shown on the different rows and indicated by the banners on the right-hand side. The value you have on the y-axis is the actual season region correction factor, and the values across the x, 1 through 12, are the month of calving, January through December. And this time the lines here aren't showing breed. Remember, these are evaluated all breeds together. 1990 is showing a group of lactation records, that's the pinkish red line, from 1990 to 94. And then the bluish line is the same thing, but 30 years later, using lactation records from 2015 to 2020. And we can simplify this interpretation a little bit by zooming in on one example, where we can say for all breeds, a cow who calved in June, so that's the middle of the peak there indicated by the 6, in the coldest U.S. climate zones between 1990 and 94, that's the pink line, requires a bigger milk correction than those who calved between 2015 and 2020. And this is actually quite good news. If we're seeing bigger corrections needed for animals in historical data, this means that we're probably doing a better job of controlling the cow's environment now, and we're not seeing the same losses in yields we used to expect with hot season and weather calvings. We can also examine the new age parity factors in the same manner. So this time, because maturity rates do vary a lot by breed, breeds are all evaluated separately. So Ayrshire, Brown Swiss, Guernsey, Holstein, Jersey, and Milking Shorthorn indicated across the top from left to right. This time, each row is a different parity. Parities 1 through 5. We did not re-estimate factors used for 6 and greater parities because those are not used in the regular genetic evaluations except in the case of productive life, so they're not shown here. Your different colored lines are once again showing 1990 to 2015. Your x-axis this time is that age, that quantitative age in months. And again, to kind of simplify interpretation here, we can look at an example with Holstein, where we see that first parity Holsteins who calve at a younger age, so that's the left-hand side, require bigger adjustments. You can see that from the slope of the line. Something that was a little unexpected for us was that the effects differ very little between time periods, and what I mean by that is that those pink and blue lines are sitting almost on top of each other. And this suggests to us that maturity rates may be a little bit more stable than we had initially expected. So we do want to encourage as widespread adoption of these new factors as possible, so the software is available for public use on our website. And this is a pretty hefty URL, so I created a tiny URL. So just /new-factors will direct you right to that site. The download file there indicates a package that has the actual program in it as well as example files, and the website itself functions as the README file. And my contact information will be at the end of the presentation, but also on this website is information of our talented programmer who put this together for you. So please use this as a resource if you're trying to use this tool and you encounter questions. So what's next? We've shown this process of looking at correcting 305 MEs, or in this case, 305 36 months, which we'll need to call them, but there's room for improvement in pretty much every single arm of this process. And so that brings me to a massive venture, a massive collaboration between CDCB and National DHIA and ourselves to update how we predict total lactation yields and estimate total daily yields. And so this is an experimental study which involves enrolling herds across the country that capture U.S. dairy systems demographics. Of course, there is more to be represented than just what I've listed here. This is our starting point with Holstein and Jersey, multiparous and primiparous animals, different grazing systems, and different milking frequency and potential robotic systems. This involves sampling cows for every single milking in their day on a weekly basis for the first 120 days of milk, and then using those weekly weights to predict their total lactation yields. And what we're trying to do here, our overall goal, is refine our prediction of actual yields as early in lactation as possible. The reason for that being that really important economic decisions are being made within the first 120 days of milk, so it's critical we provide a tool to guide those decisions about who to keep, who to cull, who to breed to whom. And we're very excited to share that this research has started. Our first pilot herd actually just wrapped up their weekly sampling. And so this involves collecting milk samples for traditional components, but also casein and fatty acids, as well as collecting all of the raw mid-infrared spectral data from the milk lab. And that's towards our secondary objective with this research of expanding their use in the prediction of alternative traits. We've also been collecting TMR samples from the same day that these milk samples are collected, because we do have a unique opportunity to relate the actual feed the cows consume with the components in the milk measured in the subsequent milkings. And all told, just in this early lactation data, we have about 68 million data points simply from our first herd. So we're very excited about this progress and what's next on the horizon. Now, of course, there's never enough time to share all the exciting things going on with you, so I want to take a minute to thank our enthusiastic industry and university collaborators who are bringing all of their talents and passion to the projects listed on this slide here. And I don't think I've forgotten any project or institution. If I have, I apologize. And I, of course, look forward to discussing and sharing some of this other research with you in the future. And so with that, I'd like to thank first and foremost dairy producers for making their data available for research use, the cows themselves for their compliance, and CDCB for their stewardship of the data and cooperation in this research. With that, I believe Kristen and I are available to take questions together, time permitting. Thank you.
Yes, good morning. Quick question about milking speed. Any information on the genetic trends we're seeing?
Genetic trends? No, that's not something that you mean over time? That's not something we've gotten to yet. This experiment does have a longitudinal design. Part of it is to answer the question, does a cow's milking speed change over the course of her lifetime? Right now, we're only able to compare primiparous with multiple parous animals, but of course there could be a big selection bias there with hard milkers being removed from the herd. So that is part of our goal, and as we start to collect data over a larger period of time, I'm sure that's something we'll be able to examine. Thank you.